Welcome to our talk titled Electrochemical Surface Modification of Titanium in Chemistry class. In the next few minutes, we will present several experiments that are concerned with the anodic oxidation of titanium metal and its uses as a surface modification method, and highlight the educational possibilities of these experiments. Before that, we will briefly look at the underlying processes that enable the titanium oxide layer growth during anodic oxidation and explain the color effects that occur because of those layers. But first, I would like to introduce myself. I am Philipp Lanfermann. I studied education in chemistry and biology at the University of Göttingen, and as of 2021, I am a PhD student in chemistry education in the group of Professor Weitz. I am also coordinator of the science outreach project for the CSC 1073 Atomic Scale Controller of Energy Conversion, and I will guide you through this presentation. Surface modification techniques play an important role in materials science and engineering to improve or extend the functionality of materials through physical or chemical alterations. Examples of such properties are adhesion, hardness, friction, biocompatibility, conductivity, or corrosion resistance, the latter two being demonstrated in experiments of this contribution. Various techniques of surface modification have been developed and established in the past decades, examples of this being found in sol-gel chemistry and electrochemistry. The importance of these processes is reflected in the fact that some of them are already part of chemistry classes, most notably the anodic oxidation of aluminum. In this contribution, we present experiments and models regarding the anodic oxidation of titanium. Despite the fact that these two processes are very similar in nature, the specific results differ greatly in optical appearance. While the porous aluminum oxide layers appear colorless and are used to incorporate dyes to fabricate colored metal surfaces, titanium dioxide shows a color impression on its own. The application of a high DC voltage to two titanium electrodes in an aqueous solution of oxalic acid leads to the formation of titanium dioxide on the anode and hydrogen gas on the cathode. The reactions at the anode are a bit more complicated in detail and shown on the right side. After the initial formation of a thin oxide layer, there is no direct contact between the metal surface and the electrolyte. Despite the fact that titanium dioxide is an electric insulator, further growth of the oxide layer takes place. The reason for this lies in the formation of mobile species which can travel through the solid. On the interface between titanium metal and titanium dioxide, titanium force species are generated and transported to the oxide electrolyte interface to form more titanium dioxide. O2- generated by this process migrates in the opposite direction towards the titanium anode. The transport of these charge carriers is driven by the electric field. The observed current and therefore the reaction rate is continuously decreasing as the layer grows in thickness, eventually reaching a stable oxide layer with no further growth. The corresponding thickness of this oxide layer is determined by the voltage used rather than the reaction time. The growth of the layer finishes in a few seconds. Longer reaction times do not lead to a significant increase in layer thickness. Using this method in our experiments, we generate layers that are between 50 and 150 nanometers thick. These thicknesses result in the interference effects with visible light producing color impressions. Incoming light is partially reflected by the outer oxide layer. However, some light travels through the transparent layer and is reflected at the titanium metal instead. This light travels an additional distance compared to the other possibility described. Thus, there is a path difference between the two light beams. Overlapping of those rays after their reflection therefore leads to interference effects. The visible color produced represents the complementary color of the wavelength range that was cancelled out by destructive interference and is also amplified by the effects of constructive interference. The visible color is directly dependent on the thickness of the oxide layer. It is therefore possible to precisely control the color by tailoring the oxide layer thickness using a defined anodization voltage. The first in a series of 3 experiments presented in our contribution is the preparation of colored titanium sheets by anodic oxidation. We use a simple 2-electrode setup to achieve a layer of titanium dioxide on the anode, making use of the process of anodic oxidation explained earlier. The setup shown at the top right also contains a digital current recorder, which is required for a following experiment. By varying the applied voltage between 5 and 65 volts in 10 volt steps, we are able to produce a broad range of colors seen in the below figure. It should be noted that smaller steps or going beyond 65 volt can yield more and different colors. While the anodes still suspended in the solution are only faintly colored, the full intensity of their appearance is revealed after rinsing and drying. Afterwards, it is also possible to measure the electrical resistance of the oxide layer using a standard resistance meter. Care should be taken to apply as little force as possible to avoid damaging the oxide layer. While the untreated titanium shows a very low resistance of several milliohms, the anodized sheet displays a resistance in the megaohm range. The direct correlation between layer thickness and applied voltage suggests that it should not matter if the final voltage is applied from the beginning or if there is a multi-step anodization. To prove this, a two-step anodization process is performed. For this, an electrolysis is carried out at 15 and 35 volts, but this time the flowing currents are recorded using digital measurement data acquisition. Afterwards, the titanium sheet anodized at 15 volts is placed back in the electrolyte and anodized at 35 volts with measured current flow. The plot shows the measured current versus time during the anodization process. As long as a significant current flows, titanium dioxide is formed and the layer grows. We can clearly see that the layer growth is mostly completed within 1 to 2 seconds, since the measured current is nearly 0 at 2 seconds. The complete lack of flowing current again proves the electrical non-conductivity of the material, otherwise there would be significant water splitting reactions at these voltages. The pictured titanium sheets also confirm our suspicion that a multi-step anodization process leads to the same results. Both sheets show the same blue color after completed anodization. The minor color difference on the photographs is overemphasized by the white balance of the used camera and therefore more pronounced in the images than to the naked eye. A visually striking use of the phenomenon of the last slide is the possibility to draw onto the titanium sheets. By anodizing at a certain voltage and drawing symbols with nail polish on the clean surface before anodizing again at a higher voltage than before, you are able to imprint those symbols onto the surface. The nail polish can afterwards be removed with acetone or household nail polish remover. As you can see in the figure below, the drawn symbols can get quite intricate if enough care is used while applying the nail polish. The last experiment shows the increased corrosion resistance of the treated titanium. Untreated and anodized sheets are suspended in hot concentrated hydrochloric acid for about 15 minutes. Afterwards, the sheets are removed from the solution, washed with distilled water and dried. As you can see in the figure, the anodized sheet remains largely unchanged despite the prolonged contact with the strong acid. The untreated sheet, on the other hand, is clearly discolored, corroded and feels rough to the touch. Even though there is a natural thin layer of titanium dioxide on the untreated titanium surface due to oxidation in air, it is not sufficient to protect the titanium from the influence of the acid. The layer formed by anodic oxidation is much thicker and is able to withstand prolonged contact. Lastly, I would like to address the educational considerations for these experiments. We believe the anodic oxidation of titanium is a suitable topic for chemistry classes to combine basic electrochemical processes, physical phenomena like interference, and industrial applications for surface modification in visually striking experiments. On the one hand, students are already familiar with products resulting from the same manufacturing method in their everyday lives. For example, titanium jewelry, spectacle frames, and many items are colored in this way. In addition, they have encountered the phenomenon of interference on thin layers. The colorful effect on soap bubbles and oil traces is based on this very mechanism. The formation of titanium dioxide layers can be integrated into the context of electrochemistry. Accordingly, in addition to basic knowledge of redox reactions, the students should be familiar with the separation of anodic and cathodic reactions in an electrolytic cell. Additionally, the practical requirements can be easily met in schools, since only titanium sheets, oxalic acid, and common voltage sources are needed. The short reaction times allow for the fabrication of a wide range of colored titanium sheets, making the experiment visually appealing. Furthermore, the discussed relation between color thickness and voltage enables the students to determine the anodization voltage used for the production of colored titanium goods in everyday life. A possible drawback could be the voltage sources used in schools, which often cannot reach voltages up to 60 volts. Instead, it can be decided to use only low voltages, since even between 5 and 15 volts distinctly colored layers are created. Alternatively, several voltage sources can be connected in series, where local regulations for science classes should be considered.